Hello friends, welcome to this lecture. Myself Amlan. Today I will discuss about alkali spectra. The elements lithium, sodium, potassium, rubidium and cesium are called alkali elements, and the optical spectra emitted by their atoms are called alkali spectra. Like hydrogen spectrum, the spectrum of each alkali element contains of a several series of lines. Among them, 4 series of lines are quite prominent. These are: first is the principal series, in which lines are quite intense. Second is the sharp series, in which lines are very fine and sharp. Third is the diffuse series, in which lines are a bit broad and diffuse. And fourth is the fundamental series, in which lines have wavelength practically equal to those of the lines of one series of hydrogen spectrum, which is considered to be fundamental spectrum in spectroscopy. Okay. Now, the wavelengths lambda of the lines of this series are given by empirical formula, somewhat similar to Balmer formula in hydrogen spectrum. Okay. Now, in sodium atom, for principal series 1 by lambda equals to R 1 by 3 minus delta S square minus 1 by n minus delta P square, and n equals to 3, 4, 5, 6 and so on. For sharp series 1 by lambda equals to R 1 by 3 minus delta P square minus 1 by n minus delta S square, and n equals to 4, 5, 6, 7 and so on. For diffuse series 1 by lambda equals to R 1 by 3 minus delta P square minus 1 by n minus delta D square, and n equals to 3, 4, 5, 6 and so on. And for fundamental series 1 by lambda equals to R 1 by 3 minus delta D square minus 1 by n minus delta F square, and n equals to 4, 5, 6, 7 and so on. Okay. Now we know here R is Ricbert constant, and delta S, delta P, delta D and delta F are numbers determined empirically. Okay. Now we note that these series formulas are somewhat similar to hydrogen spectrum. Okay. But the numbers delta S, delta P, delta D and delta F, which causes the difference. Okay. For this is for sodium atom. Okay. Now for other alkali atom, these series formulas are of the same form. For example, for lithium, in place of 3 there will be 2, and the minimum value of n is 2, 3, 2, 3. Okay. And suppose for potassium, instead of 3 there will be 4, and minimum value of n is 4, 5, 4, 5. Okay. Now, obtaining the alkali spectra in high resolving power spectroscope, it has been observed that each lines of principal series and sharp series is a doublet, that is consists of 2 close lines, and each lines of diffuse series is a triplet, that is consists of 3 close lines, and the lines of fundamental series do not show such splitting. Okay. Now we explain the origin of these 4 series lines of alkali spectra. Okay. Now we explain the origin of these 4 series lines of alkali spectra. Now the atoms of all alkali metals have similar electronic configuration. An atom of each of them consists of a number of electrons in the closed cells or subcells and a single s electron in the outermost cell. The vector sum of angular momenta and magnetic moments of all the electrons in the closed cells or subcells is 0. So these electrons form a stable structure, okay, and the single s electron in the outermost cell is responsible for the chemical and optical properties of the atom, okay. So this electron is called valence electron or optical electron, okay. Now, in an alkali atom with atomic number Z, the Z-1 number of electrons in the closed cells or subcells partially screen the nuclear charge from the optical electron, okay. If all the electrons in the closed cells or subcell would move in a circular orbit, then to the optical electron, the effective charge of the nucleus will be plus Zd minus Z minus 1 into E, that is plus E, okay. And so from the optical point of view, the structure of the alkali atom would be similar to that of the hydrogen atom, and so the energy value will be E equals to minus RHc by n square, okay. Suppose this is equation 1, okay. Now here n is principal quantum number, R is Ricbert constant, H is Planck's constant, okay. Now actually all the electronic orbit are not circular. Suppose this is nucleus of charge plus Zd, okay, and this is the orbit corresponding to n equals to 2 and L equals to 1, and suppose this is the orbit corresponding to n equals to 3 and L equals to 1, okay. Thus we see that the orbit of an electron with n equals to 3 and L equals to 1 is elliptic, and a part of this orbit penetrates into the inner orbit with n equals to 3 and L equals to 1, okay. Now when the optical electron in the orbit with n equals to 3 and L equals to 1 traverses through the penetrating part of this orbit, the screening effect of the electron in the inner orbit is reduced, and so the nuclear charge effective to the optical electron on time average is increased from the value plus E, okay. As a result, energy becomes more negative than the value given by equation 1. The same effect is obtained by subtracting a suitable number delta from n in the equation 1, okay. So now equation 1 is modified as E equals to minus RHc by n minus delta square. Suppose this is equation 2. The number delta is called quantum defect, okay. delta is called quantum defect. Now we draw the energy levels of the optical electron in a sodium atom in various energy states. Okay. Now we draw the energy levels of the optical electron in a sodium atom in various energy states. Suppose this is 3s level. Okay, this is 4s level, this is 5s level, this is 6s level, and this is 7s level. Okay, now suppose this is 3p level, this is 4p level, this is 5p level, and this is 6p level. Suppose this is 3d level, this is 4d level, this is 5d level. Okay, and suppose this is 4f level and this is 5f level. Okay, now the transition from 3p level to 3s level and the transition from 4p level to 3s level and the transition from 5p level to 3s level gives rise to the lines of principal series. Okay, now here in our case the selection rule is delta L equals to plus minus 1. So in this case the transition from 3p level to 3s level gives rise a spectral line, and the transition from 4p level to 3s level gives rise a spectral line, and the transition from 5p level to 3s level also gives rise a spectral line according to selection rule delta L equals to plus minus 1. Okay, now this transition gives rise to the lines of principal series. Okay, so this is principal series. Now the transition from 4s level to 3p level, transition from 5s level to 3p level, and the transition from 6s level to 3p level gives rise to the lines of sharp series. Okay, so this is sharp series. So according to the selection rule delta L equals to plus minus 1, the transition from 6s level to 3p level, 5s level to 3p level, 4s level to 3p level gives rise to the lines of sharp series. Now the transition from 3d level to 3p level, 4d level to 3p level, and 5d level to 3p level gives rise to the lines of diffuse series. Okay, so this is diffuse series, and the transition from 4f level to 3d level and 5f level to 3d level gives rise to the lines of fundamental series. Okay, so this is fundamental series. So these are the 4 series lines of alkali spectra in a sodium atom. Okay. Now we explain the doublet structure of the lines of the principal series and sharp series and triplet structure of the lines of the diffuse series. Okay. Now Now we explain the doublet structure of the lines of the principal series and sharp series and triplet structure of the lines of the diffuse series. Now to explain the doublet structure of the lines of the principal series and sharp series and triplet structure of the lines of the diffuse series, Uhlenbeck and Gaudsmit gave the hypothesis that an atomic electron has a spin motion in addition to the orbital motion. This hypothesis is one of the bases of the vector atom model. Now according to the vector atom model, an atomic electron has a spin motion, angular momentum PL, and has a spin angular momentum PS, and so total angular momentum Pj equals to PL plus PS. Okay. And their magnitudes, suppose this is vector, this is vector, this is vector. Okay. An optical electron has a orbital angular momentum PL, spin angular momentum PS, and so total angular momentum is Pj equals to PL plus PS. And their magnitudes are PL equals to modulus of PL equals to root over L into L plus 1 into H cut, where L equals to 0, 1, 2 to N minus 1. Okay. And PS equals to root over S into S plus 1 into H cut, and S equals to half for optical electron, and Pj modulus equals to root over J into J plus 1 into H cut, where J equals to S, J equals to 0, J equals to S when L equals to 0, and J equals to L minus S and L plus S when L does not equals to 0. Okay. So this is modulus of PL vector, and this is modulus of PS vector, and this is the modulus of PJ vector. Okay. Now the magnetic dipole moment mu L vector due to the orbital motion of the electron is given by mu L vector equals to minus E by 2me into PL vector, and the magnetic dipole moment mu S vector due to the spin motion of the electron is given by mu S vector equals to minus 2 modulus of E into 2me into PS vector. Okay. Now due to the spin orbit coupling, PL vector and PS vector undergo precession about the direction of Pj, and as a result a small term involving N, L, S and J is added to the electron. Okay. Now in the S state of the electron, L equals to 0, and so J can have single value half. Okay, so each A state energy level is a singlet, and in the P state A equals to 1, and so J can have two values, half L minus S and L plus S, that is J equals to half and 3/2. In the D state L equals to 2, and so J can have two values, 3/2 and 5/2. And in the F state L equals to 3. J state L equals to 3, and so J equals to 5/2 and 7/2. Okay. Now we draw the energy levels of the optical electron in a sodium atom. Splitted energy level of the optical electron in a sodium atom. Okay. Suppose this is 3s half level, this is 4s half level, this is 5s half level, this is 6s half level, and this is 7s half level. Okay. Now 3p level is divided into two sub levels. Suppose this is 3p half level and this is 3p 3/2 level. Also 4p level also divided into two sub levels. Suppose this is 4p half level and this is 4p 3/2 level. Now 5p level also divided into two sub levels. Suppose this is 5p half level and this is 5p 3/2 level, and 6p level divided into two sub levels. This is 6p half level and this is 6p 3/2 levels. Okay, so these are the splitted energy levels. This is 3p, 4p, 5p and 6p energy levels. Now 3D energy levels also divided into two sub levels. Suppose this is 3D 3/2 level and this is 3D 5/2 level, and 4D level also divided into two sub levels. This is 4D 3/2 level and this is 4D 5/2 level, and similarly 6D level also divided into two sub levels. This is 6D 3/2 level and this is 6D 5/2 level. Okay. Now similarly 3F level or 4F level also divided into two sub levels. Suppose this is 4F 5/2 level and this is 4F 7/2 level, and suppose this is 5F 5/2 level and this is 5F 7/2 level. Okay, so these are the various splitted energy levels in a sodium atom. Now here selection rule is delta J equals to plus minus 1 and delta L equals to plus minus 1 and delta J equals to 0 plus minus 1. Okay, so these are the two selection rules. So the transition which satisfy these two selection rule, that is delta L equals to plus minus 1 and delta J equals to 0 plus minus 1, do actually occur. Now the transition from 3p 3/2 level to 3s half level gives rise a spectral line, and the transition from 3p half level to 3s half level also gives rise a spectral line. These two transition gives rise to the lines of principal series. Okay, so this is principal series. Now the transition from 4s half level to 3p half level, 3p 3 by 2 level gives rise a spectral line. Also the transition from 4s half level to 3p half level also gives rise a spectral line. Okay, transition from 4s half level to 3p 3 by 2 level gives rise a spectral line, and transition from 4s half level to 3p half level also gives rise a spectral line. These two spectral line gives rise to the lines of sharp series. So this is sharp series. Now the transition from 3d 5 by 2 level to 3p 3 by 2 level gives rise a spectral line, and the transition from 3d 3 by 2 level to 3p 3 by 2 level also gives rise a spectral line, and the transition from 3d 3 by 2 level to 3p half level also gives rise a spectral line. Okay, thus these three transition gives rise to the triplet component of the lines of diffuse series. Okay, so this is the triplet component of diffuse series, and these two transition gives rise to the doublet component of the lines of principal series and sharp series. Okay, now the transition from 4f 7 by 2 level to 3d Now the transition from 4f 7 by 2 level to 3d 5 by 2 level gives rise a spectral line. Now the transition from 4f 5 by 2 level to 3d 5 by 2 level also gives rise a spectral line, and the transition from 4f 5 by 2 level to 3d 3 by 2 level gives rise a spectral line. Okay, so there are three allowed transition. Now the energy difference in the three permitted transition, that is 4f 7 by 2 to 3d 5 by 2, 4f 5 by 2 to 3d 5 by 2, and 4f 5 by 2 to 3d 3 by 2. In the three permitted transition, the energy difference are so small that the triplet component of the lines of the fundamental series is not detectable. Okay, thus so these are the two doublet component of principal series and sharp series, and this is the triplet component of the diffuse series. Okay, thus we explain the doublet component of the principal series and sharp series and triplet component of the lines of diffuse series. Okay, thank you for watching this video.